Hello everybody, this is Homer White back again with the second part of the 10th chapter of our course. We're working on tests of significance. In this part, we're going to make explicit the relationship between tests and confidence intervals. But we're also going to talk about how confidence intervals overall are more informative and give you an advantage over just the results of a significance test. Always remember to make sure the necessary packages are loaded. Let's look now at the relationship between tests and intervals. Remember the fundamental difference between the two. Confidence intervals answer the question, given the data, within what range of values might the parameter reasonably lie? And tests of significance answer the question, given the data, is it reasonable to believe that the parameter is a particular given value? Let's take an example. Say we're testing two hypotheses. The null is that some population mean is equal to 100, and the alternative is that the population mean mu is not equal to 100. And say when we take our sample, we get the following summary results. The sample mean x bar turns out to be 101. The sample standard deviation s turns out to be 6, and this was on a sample of size 36. Let's run our two-sided test and get a 95% confidence interval along with it, using the usual code. So we have summary data. So we say that our sample mean is 101, the sample standard deviation is 6, sample size n is 36. We need to specify that the null hypothesis is that mu is 100. And since we are asking for a 95% confidence interval, we don't have to set a confidence level. And since we're asking for a two-sided test, we can just accept the default two-sided value that will come out from t-test GC. So we get this confidence interval that extends from 98.96 to about 103. Notice that 100, which is the null hypothesis's belief about mu, is inside this 95% confidence interval. The p-value for the test turns out to be about 0.32. That's bigger than 0.05, so we're not going to reject the null. The null's belief was inside the confidence interval, and we are not rejecting the null. Now a slightly different example. Say we're testing the same hypotheses, but the summary results we get are a little different. Let's say the sample mean x bar is 102.5 instead of 101. But we have that same sample standard deviation s off of the same sample size, 36. Again, try the same basic code, except now the sample mean is 102.5. This time the confidence interval that we get extends from about 100.4 to 104.53. Notice that this time 100, which is the null's belief about mu, is outside of this confidence interval. Notice also that the p-value is 0.017, and that's less than 0.05. So we're going to be rejecting the null hypothesis. The null was outside the 95% confidence interval, and our p-value turned out to be less than 0.05. What we have is this fact that always holds true, not just for the examples we've studied. Suppose that you plan to make a 95% confidence interval for the parameter of interest, and let's say the null thinks that that parameter is some particular value mu naught. Then if you find that mu naught lies outside of your 95% confidence interval, then the p-value will always turn out to be less than 0.05. On the other hand, whenever mu naught lies inside that interval, then the p-value will turn out to be more than 0.05. Here's another fact that always holds true. Suppose that you plan to make a 90% confidence interval. And again, suppose the null thinks that mu is some particular value mu naught. If mu naught lies outside the interval that you produce, then the p-value will be less than 0.10. If mu naught is inside the interval, then the p-value will be more than 0.10. 95%, 0.05. 90%, 0.10. Are you starting to see a pattern? Here is the relationship between test of significance and confidence intervals in general. Let's let alpha be some proportion, some number between 0 and 1. And let's say that you plan to make a 100 times 1 minus alpha % confidence interval. And the null thinks that mu is some particular value, mu naught. If mu naught is outside the interval, then the p-value will be less than alpha, and if mu naught is inside the interval, then the p-value will be more than alpha. This result covers the two previous facts that we've already looked at, and infinitely many more as well. If you were to think of the alpha as 0.05, then 1 minus alpha would be 0.95, and 100 times that would make 95% confidence interval, and then if you lie outside the interval, the p-value is less than 0.05, and if you lie inside the interval, then the p-value is more than 0.05. So you see how this fact generalizes the fact about 95% intervals and a 0.05 cutoff. In a similar way, it generalizes the fact about 90% intervals and a 0.10 cutoff. So there's obviously a close relationship between test significance and confidence intervals. But all in all, confidence intervals have some real advantages. First of all, confidence intervals tell you at least as much as a test of significance does. A confidence interval can predict the result of a test of significance even before you see the p-value of the test. Suppose the confidence level matches the cutoff value. So say that you've asked a t-test GC or some other R test function for a 95% confidence interval, and you plan also to have a 0.05 cutoff value. And I'm sorry, the percent should not be there. Or say that you're asking for 90% confidence interval, and you plan to reject the null hypothesis when p is less than 0.10. So say that you have matching confidence levels and cutoff values in some way like this. Because of the relationship between confidence intervals and tests that we have just discussed, you can tell just from the confidence interval and whether or not mu naught lies in or outside of it, how that test is going to come out. Here's another consideration. We have to work our way up gradually to it, though. So let's take another example. Suppose you are interested in the difference of two population means, mu1 minus mu2, and you're testing whether or not that difference is 0 or different from 0. So a two-sided test. And let's say you take your first sample, and the sample mean turns out to be 100.1, and the sample standard deviation is 6, the sample size is 36, and say you take your independent sample from that second population, and the sample mean turns out to be 100, not much different than for the first group. And let's just say that the sample standard deviation was also 6, and that the sample size was also 36. So you might try out t-test GC. This is summary data, and so we put in for the mean the list of the two sample means that we've got. For the standard deviation argument, we put in the list of the two standard deviations that we got. And for sample sizes, we put in the list of the two sample sizes we got. The null hypothesis thinks that mu1 minus mu2 is 0, and so we set the mu argument to that. By default, we'll be looking for a 95% confidence interval, and here we go. So the 95% confidence interval extends from about negative 2.7 to about 2.9. Clearly, 0 is inside that interval. We're not going to be rejecting the null hypothesis. And in fact, the p-value is bigger than 0.05. In fact, it's quite large. It's about 0.94. So essentially no evidence in these two samples for a difference between these two population means. Now let's make things just a little bit different. Suppose you're still running the same test on mu1 minus mu2. But this time you take much larger samples, 36,000, from each population. Let's say that you still have a very narrow difference between your sample means, 100.1 for the sample mean from the first population, and 100 for the sample mean from the second population. That's the same difference between sample means that we saw in the first example. It's just that this difference occurs at a much bigger sample size. So you run the code on this summary data. The only thing that changes is that the sample sizes are much bigger. Now look at your 95% confidence interval. It's quite a bit narrower. It extends from only about 0.01 to about 0.19. But it does not contain 0. So we know that at a 5% level we're going to be rejecting the null hypothesis, and in fact the p-value does turn out to be less than 0.05. It's only about 0.025. So wow, we're going to reject the null hypothesis. This time we've got strong evidence for a difference between the two population means, mu1 and mu2. But think again about that confidence interval. We're pretty sure that mu1 minus mu2 lies in between these two numbers. That range consists of numbers that are pretty close to 0, all of them. So this lets you know that the difference between mu1 and mu2 is probably very small. In your practical situation, it may not be important at all. So you always need to keep in mind that at very large sample sizes, you can acquire a lot of evidence for a very small difference. Tests of significance are a lot like a microscope that has different settings. And the most powerful setting is at large sample sizes. At large sample sizes, if the null hypothesis is just a little bit false, you can pick up on that falsity in your huge samples, even when that falsity is itself a very small size. So don't always get excited by low p-values. Low p-values do indicate strong evidence that the null is false, but you might just have strong evidence that the null is a tiny bit false. Confidence intervals are what keep you really focused on what's important, because they keep the effect size clearly in your mind. Thank you for listening.